Okay. Sabrish has a question, or he's okay. Try speaking by fixing your issues. Otherwise, that's okay. He says that when we use this function called random equal to some number, then in this line, random state equal to something. Okay. Then each time I split, I'm going to get the same training and test data. Then how can it become a disadvantage? Wherein each time I split the data into training and test, if the training and test data is going to be the same, then where is this problem going to arise? I'll ask you the same question. If I'm going to each time going to have the same data, why do I need to again split it in the first place? If I split the data, each time if I'm going to use random state equal to 0, what will happen? Next time when you try to split, when you try to run this line, it will give you the same data. Each time if it's going to give me the same observations in training and test, why do I even need to split it again second time? The rationale behind taking different training and test data each time is to experiment and to understand whether your algorithm that you've built, does it work well on each different splits or not? That's the idea. Simple. When I build a model on a specific data set, and when I test it on a test data set, it will give me some accuracy. Can you guarantee that next time if I have different data set in test, it's going to give me the same accuracy? If I give you a different test data again, will it give me the same accuracy? If it is not going to give me the same accuracy, then can I rely on the model that I built? Because my model is going to give me different accuracy values each time. Okay, when I test it on the test data. Making sense? If I have different test observations, different test data sets, if it's giving me more or less the same accuracy, fine. I'm okay with that. But somewhere it gives me 90%, somewhere it gives me 70%, again, probably it gives me 80%, then the variation is too high. That means the model that I built, it's not working well on all of these. And I cannot guarantee that each time it's going to give you more or less 80%. I cannot guarantee that. Since you cannot guarantee that each time you're going to get more or less 90% accuracy, what people ideally do is they run it multiple times, take an average, and they say that on an average, this is the accuracy that you get. Okay. But when they do this, they also split training data because they want to see what if I have a different data set in training and different data set in test, would the model accuracy values be more or less the same? Or are the model accuracy values going to fluctuate a lot? If it's fluctuating a lot, what should you do? You just take average of all those and say that this is your final accuracy. Making sense? Sabrish, making sense? Okay. Siddhant, you need to check with the concerned teaching associate for that. Coding related errors. Okay. So we have ensemble techniques, and ensemble techniques are used basically to solve the variance bias trade-offs. Point number one. Point number two, the basic premise here is to use multiple models or techniques and then combine the results into one. This is the basic premise with which Ensemble algorithm proceeds further. In sample means the data which is in training, which is used to train your model. Out of sample is that data which is not in your training, which is test data. In sample is also called as in bag. Out of sample is also called as out of bag, which is also called as OOB. Okay. Next. Ensemble techniques can be used for all of these purposes: diagnostics, regression, classification, survival, time series, so on and so forth. It works well usually when you have large data set and non-linear data sets. Then it has two steps. One is building the model, another is combining the model. Ensemble means multiple models. You build multiple models. Then what is the next step? Combine the results of all of those. These are the two things, right? So base learner means the individual algorithm that you're going to run. If you use the same base learners, so if you say that I'm going to use only decision tree algorithm, I have data. I'm going to split this data into training and test. Okay, and then I'll build a model, decision tree 1. I get some accuracy, say 90%. Again, I'm going to split this data into training and test. Again, I'll build the model on training, test on test. So I have decision tree 2. Probably this will give accuracy of 80%. Again, I'm going to split the data into training and test. Build the model on training and test it on test. This is decision tree 3. Again, I'll get some accuracy. How can I combine these results? By taking a simple average. 90 plus 85 plus 80 by 3 will give me a simple average. Okay. If you use the same algorithm throughout, it can be decision tree algorithm only, it can be KNN algorithm, it can be any other algorithm. If you use the same algorithm to train on each and every split, then it's called as homogeneous ensemble model. But sometimes you might say that on this first split, I will run support vector machine. Second split, I will run decision tree. On the third split, I'm going to run neural networks. So if you use different algorithms on different splits, and then if you want to take average of the accuracies, it's called as heterogeneous because you're using different algorithms. You're using different base learners. Those individual algorithms are called as what? Base learners. Okay. All right. Give me a minute. If I just checking whether I can get some additional information for you guys. I made a note of all the important things. I don't want to miss out on anything. In sample, out of sample, we discussed. Okay, and one more thing is the reason behind splitting the data multiple times is each time when you randomly split the data, maybe the kind of observations that you get in training and test might not always give you a good model. Your model building means what? Learning the patterns in your data. I have the overall data. When I split that into training and test, I cannot expect always good quality data to be in training, good quality data to be in test. Each time I split, the kind of accuracy that I get also depends on the observations that I have in training and test, because ultimately a model is learning the patterns. What if your split is very bad or very different? Randomly you're splitting. I'm not at all discounting the thought that you're randomly splitting. But sometimes, very rarely, it might so happen that training data might be very different to your test data. So when you build your model on training data and test it on test data, you might get bad results. Sometimes your training and test data might be so close to each other, perfectly maybe it is split. And hence, when you train your model and test on test data, your accuracy is very high. Can you expect that always? No. To remove that 1% chance or very small percentage chance of having very good data, very good split into training and test, or very bad split into training and test, you split it multiple times. And you run the model multiple times so that you bring in some kind of consistency into your model. That's another reason why we build multiple models multiple times by splitting it multiple times. Okay, that's one more point that you will have to remember. And in sample, out of sample is done. Okay. One more very important thing is we have something called as generative versus non-generative algorithms. Generative versus non-generative. Okay. Write down. When I'm explaining about a concept, don't assume you'll remember everything. You're not robots, so please make a note. Okay. Generative versus non-generative. When it comes to non-generative algorithms, you have two things. One is called as voting. Okay. Another is called as stacking. Okay. So stacking, we will deep dive. Voting also, we are going to deep dive. So I'll just hold on rather than explain more things. And here, generative are your boosting models. Suppose you are running homogeneous algorithm. If you're saying that run this algorithm 10 times, what will it do? It will split the data into training and test 10 different times. And it will train 10 different times, test it 10 different times on the test data, right? Here, one algorithm versus another, there is no relationship. They're all standalone algorithms. If you're saying run algorithm 10 times, 10 different algorithms are built. Of course, they are all decision trees, but all these 10 will be trained on 10 different training data sets and tested on 10 different test data sets. So each one is different. You just combine the results of all the accuracies. Okay. Those kind of algorithms are non-generative. But there will be algorithms where there'll be dependency of one algorithm on another. Say you split the model, you built one algorithm. Then next time when you split, the next split depends on the first algorithm results. How it will depend, all that we'll discuss, we'll deep dive. You built an algorithm, right? 10 times you need to run, first time you have run. Second time when you split the data into training and test, the second time when you're splitting, how you split depends on the first algorithm results. So when there is dependency of one algorithm on another, it is called as generative. From one, you're generating second algorithm. From the second, you're generating third algorithm. From third, you're generating fourth algorithm. Okay. So one algorithm, you understand what are the challenges. One algorithm, when you run, what are the challenges? When you split the data again, it might give you completely different results. That's a challenge. Hence, what are we doing? We are resorting to ensemble. Within ensemble, we have homogeneous and heterogeneous. And you have generative versus non-generative. Here, bagging is also called as generative. Why? We will understand. And we have random forest. Okay. So you have generative, non-generative. In non-generative, you have voting and stacking. In generative, you have boosting, bagging, and random forest. Okay. So uh, no, it can be heterogeneous also. But people don't usually do that. They go with homogeneous only. Why you can, it doesn't make sense. So they go with homogeneous. Okay. So next thing, but why do people not use ensemble techniques in that case? So the greatest advantage, okay, first thing I'll talk about advantage. Advantage with respect to ensemble technique is that accuracy will be very high. Why do you think accuracy will be very high? Because you're running multiple times. First time when you run, algorithm might say person has cancer. Second time when you run, it might say no cancer. Third time it might say no cancer. Fourth time also no cancer. So you can always take that majority. Majority will not go wrong, right? If I ask a question to 100 people, out of 100 people, 80 people are giving me a specific answer. That will not go wrong because you're going with majority, simple. Right? That is another rationale why ensemble techniques give you good accuracy. Then why shouldn't I use that? Because of two reasons. One is it'll be time consuming process. If I run an algorithm one time, it might get completed in 1 second. If I run the same algorithm 10 times, it will be more than 1 second, right? Obviously. One algorithm, if I run once, it's getting completed in 1 second. In 1 second, I'm getting the result. If I run the algorithm 10 times, obviously the final result will not be displayed in 1 second. It will be more than 1 second. So it'll be time consuming. Second thing is, so let me remove these. Greatest advantage with ensemble technique or techniques is that accuracy will be high. Second thing is it will bring some stability into the algorithm because your accuracy values will not fluctuate a lot. Stability also will be high. However, what is the disadvantage? These are the pros. What are the cons? Time consuming. Absolutely, it'll be time consuming, no doubt about that. Second thing is, if I run one decision tree, you can look at that rule, classification rule, which is this rule. Everything is a single rule, right? You can look at these rules and it is pretty self-explanatory, right? Income is medium and not a student and age is in between 31 to 40, person will buy a computer. So it is pretty self-explanatory. If I run hundreds of these models, then what will happen to your explainability or interpretation? It will become difficult. One algorithm, it's very straightforward. You're saying combine 10 such algorithms and 10 such classification rules, what will happen? Your interpretation will become difficult. So that's one disadvantage with interpretability decreases. These are the disadvantages. Okay, next. Okay, so next thing is with respect to the two steps. Here we didn't complete the two steps. One is either you build the same base learner or a different base learner. It's up to you. Once you build the model, how do you combine the results? Either using voting technique or averaging technique. Within voting, you have hard voting and soft voting. Hard voting means if for specific input, wherein you have age, gender, income, etc., and you want to classify whether a person will default or not. If you're giving these inputs to your model, okay, one decision tree model might say person will default. Another decision tree model might say person will not default. The third one might say person will not default. Fourth model also might say person will not default. Then what do you take out of all these? What should be the final answer? Not default. So you're doing a hard voting. Final output is dependent on the majority, maximum votes. Simple. Then you have soft voting. Soft voting is applied when you get probabilities as output. There's 90% probability that person will default. There's 84% probability that, or here, let me say there is 16% probability that person will default. That means there is 84% that person will not default. And here, if I say there's 90% probability that person will default, then what is the probability that person will not default? If I say there's 90% that person will default, what's the probability that person will not default? 10%. Here, say there is 90% probability that person will not default, 84% probability that person will not default, then probably 96% probability that person will not default. When you take all these, take an average. What do we get if we take an average? Anyone? Can you help me? 50%, is it? Let me say 20%. Then how much do you get? Sorry, 70%. There's 70% probability that person will not default. So what will be your ultimate result? Not default. Okay. So in that way, you just take average of all the probabilities and then take a decision on them. This soft voting can also be used when your output variable is continuous. What will be the salary of the people? who submitted all the assignments, attended all the classes, worked on live projects, right? What would be the salary? One algorithm might say that salary would be 10 lakhs per annum. Another, algorithm might say salary will be 9 lakhs per annum. Another algorithm might say that salary would be 12 lakhs per annum. So ultimately, what do? You take an average of all these, and that would be the final salary. Okay, so that's called as soft voting. Hard voting is used usually when you have classification problems. Soft voting is used when you have output variable which is numerical. When output variable is numerical, the underlying problem is called as regression problem, friends. When your output variable is categorical, the problem is called as classification problem. Okay, classification problem or regression problem. Okay, voting is one thing. Then we also have averaging. One is simple average, another is weighted average. Usually averaging is used when you have regression problems. Regression problems means output variable is numerical in nature. Weighted average means give more weightage to those algorithms which give you high accuracy. Give less weightage to those algorithms which give you less accuracy. That's called as weighting average or weighted average technique. Okay. So what are the two steps in Ensemble techniques? You build various models and you combine the results, which is the second step. These are the two steps. Build different models, combine the results. These are the only two steps which are involved. So we now understand generative, non-generative. Within non-generative, we have voting and stacking. Within generative, we have boosting, bagging, and what else? Random forest. Okay. Then we have sampling techniques. So what we will do is we will have probability, non-probability, cross-validation, bootstrapping. Okay. Then we will get into bagging. After bagging, we will get into random forest. I think until random forest, we will be able to complete. And tomorrow when we connect, we will be able to talk about boosting and stacking. With that, affirmatively, we should be able to conclude. Okay, these sampling techniques, let us talk about. Okay, we would rather, this is a new technique, right? So let's take a break, lunch break, and then once we are back, we will get into this discussion.